Good morning, everyone. Now we are going to start our next topic, that is Bravais lattices. We have completed in the last class. First of all, we'll have a brief introduction in the last class, what we have completed. In the last class, we have done the topic related to the crystal lattice, right? And what we can say, what is actually the meaning of crystal lattice? See, so this was our first slide for the class 2. So there is, see, the crystal lattice, we have done that the periodic arrangement of the points are nothing but we'll call such arrangement as crystal lattice. So in the later section, we have just gone for the crystal structure. So how you know the crystal structure? So when you add this basis plus lattice, you'll get the whatever the image or the pattern you will get, that is called crystal structure. And how the two-dimensional picture of Bravais lattice we can just see. I already told you that Bravais is a scientist name who has discovered this arrangement, periodic arrangement of points. So therefore that is called Bravais lattice. So Bravais lattice plus basis will give you crystal structure. So how this Bravais lattice look like hexagonally? So in hexagonal, the lattice arrangement will be like this, what we have seen in the previous class. And how the crystal structure is there. So this also we have seen. So I've already told you these are nothing but the crystal lattices, and these are the blue color is crystal lattice, and the color which is seen to you adjacent to the blue color, that is red color, that is actually the atoms or molecules or the ions. And when we combine this together, so whatever the image or the pattern will get, that particular pattern is nothing but crystal structure. Now, so in the previous class we just discussed about the crystal lattice, different types of crystal lattices, that is Bravais lattices, non-Bravais lattices. So what is the actual geometrical figure from which we can understand, right, Bravais lattice? So you already learned about this in the last class, that this periodic arrangement. If you find this particular arrangement of the atoms, so just call such particular arrangements known as Bravais lattices. And what are non-Bravais lattices? These are the, if this particular arrangement is in this particular fashion, so this is called, we'll call such arrangement as the non-Bravais lattices. So now, so again we have in-depth study about the Bravais lattices. We have taken the example of niobium film in the last class. So where we have shown that this arrangement, you can just see the arrangement. See this particular image which I have taken. See this particular thing which has been shown to you. So this is the arrangement, hexagonal arrangement. Now we can see this is the orientation of infinite array of some discrete point. We call that as Bravais lattices. And how two-dimensionally, when I join these points, how two-dimensionally the crystal lattice structure, crystal lattice, how it look like. It is two-dimensionally, it is in this particular format. So now we have taken the example of honeycomb. So honeycombs for the non-Bravais lattices. How the arrangement of the points for non-Bravais lattices. So we have taken the example of honeycomb, and then we come across the translation lattice vector. Why we are studying about this translation lattice vectors? That we have already learned in the last class. Why? Because actually, see, whatever the imaginary part or the thing that whatever we have assumed, so that should be proved mathematically. So these particular arrangement is given by the mathematical form Rn is equal to Na A plus N to B. Now this particular arrangement will call such as translation lattice vectors two-dimensionally look like this, and this three-dimensionally the structure will be like this. This is the unit cell structure three-dimensionally. So where you can just see that when you combine these points, and these points are nothing but you can just see this dash lines. And when we join these dashed lines, so whatever the structure we are getting, that structure is nothing but it is a unit cell cubic. Unit cell is in the shape of cubic crystal. So now, so in the last class again we have discussed about the Bravais lattices. So how many types of Bravais lattices which is available two-dimensionally? So we can just take an example of general way. So by which this particular figure indicates that the arrangement of the lattice points in this manner. So which indicates that the identical way of arranging the lattice points such that the environment about each point is same. So now this is, you can just see this is a general arrangement of the points, rectangular, square, hexagonal, centered, rectangular. These type of arrangement of these points are nothing but, this is a 5 Bravais lattices in 2 dimension. So in 2 dimension, to find that unit cell in 2 dimension, this is the shape of unit cell in 2 dimension. And then see here. So these particulars, you can just see what is this S. S indicates your stacked spaces, which will be structure of your unit cell. So these particular things. So the choice of unit cell is exactly not exactly whatever you like. So it is not unique. So you can just take. See, we have taken the example of like this. See, so you can just mathematically, geometrically, you can just we can see the structure of the unit cell in 2 dimension. This is the way different patterns, how unit cell can be arranged and how the unit cell look like 2 dimensionally, right? So now this is we have taken the example. Now this is a schematic diagram of any crystal. Because when we talk about any crystal, so we are not naming a particular component or the material. So that is the reason that we have just indicated with this different arrow marks. Now, when we just take an example of NaCl, the common example that we are taking a sodium chloride crystal. So here, the arrangement of the atoms, you can just see the periodic arrangement of the atoms inside the NaCl. So we define these lattice points are nothing but they are having the identical environment. So see here, you should not get confused that if I say lattice points for atoms, right? Actually, we are just indicating these lattice points again in the later section with the constituent particles, and that constituent particles are nothing but lattice points, right? So first of all, we need to understand the imaginary point, then we are associating that imaginary point that are nothing but the lattice points with respect to the constituent particles. Now this origin is arbitrary, means you can just take a reference point such that you will get this type of structure what we have just seen in this previous. You can just see again, I'm showing you like this, right? So these references point, different reference points what we have taken. See, here the reference point is this, here the reference point is this, and this is the reference point for the third one, and this is the reference point for the fourth one. So like this, you can have an arbitrary reference points. So see, that is the reason that we are just considering the origin as arbitrary. Lattice points need not be the atoms but unit cell. So what it indicates? Just now I told you that lattice points need not be atoms, means it may be atoms or it may be ions or it may be molecules and so on. So see, this is also a unit cell. See, again we say that it is not unique, but the reference point is important. So it doesn't matter if you start from sodium or a chloride right atom. So if it is a sodium atom or chloride atom, so you will find that unit cell look like this in 2 dimension. So this is the arrangement of 2 dimensional arrangement of the smallest geometrical figure. So that is nothing but unit cell. So here this particular is not unit cell, even though they are all the same. You can just see we cannot say this is a particular unit cell, right? So why, sir? So unit cell will not have any empty space. Here empty space is not allowed. You find that here there are empty spaces. You can just see every atom are not closely arranged. See, this blue and this orange or red, whatever you are seeing, these particular 2 atoms are having empty spaces. So this is not, I cannot say that is a perfect unit cell. It is not a unit cell since it is having a space. So therefore, so in 2D this is a unit cell, and in 3 dimensional it will not be a unit cell. So now again when I say, see, these particular points will find that in 2 dimensional this is the case, and when we move to the 3 dimension, we can just see that this is the different. See, you can just see this particular figure. See here, this is a cubic in shape, and this is having, see how many unit cell you are having. They see you cannot exactly count it. So this numerous number of unit cell, combination of the numerous number of unit cell will give you the exact crystal structure. Again, in the last class we just got started with the atoms, and then the combination of these atoms are nothing but molecules. Again, when these molecules are combined, and if we join these molecules with a line segment, so it is taking the shape, whatever the shape it is taking, what is the smallest geometrical figure which is taking, coming into existence, that is what unit cell. And these collection of unit cell, you can just see, this unit cell is only a single isolated one. So these type of isolated unit cells, you are having numerous number of unit cell here. You see, you can just imagine this, right? I'm talking about these all unit cells. So here, so this is 3 dimension. So in the last class, we just started with the common unit cell which is found in 3 dimension for a cubic crystal. So when I say cubic crystal, most of the crystals which is available on the earth crust, you will find that most of it are having cubic in nature. And definitely you will have more examples in order to understand why I am particularly talking about the uh, cubic crystal system or cubic unit cell. So you will come to know in the later classes, so why we are concentrating or we are giving due importance to the cubic cell, unit cell. And also, so when we see this particular figure, you can just, in the last class we have just shown you this unit cell, and the figure is in this particular format. And in body centered, you are having a particular atom exactly at the center, and in the face centered cubic, you are having at the faces one atoms which are residing at the faces of the unit cell. Now, so unit cell, we just started with the unit cell. We just started with the unit cell, and these unit cell is again been classified depending upon the arrangement of the lattice points. In the unit cell, they have been classified into 2 different categories. That categories are nothing but primitive, or we can say conventional and non-primitive, or we can just say non-primitive and non-primitive unit cell. So when I say primitive unit cell, so single lattice points which are available per cell are the smallest area in 2 dimension or the smallest volume in the 3 dimensional. We just call such arrangement as nothing but primitive. See, we are taking an example here for 2 dimension. When we see 2 dimension, so I have taken example of NaCl also. In the previous slide, I have shown you this particular figure indicates the unit cell of 2 dimension, and this particular figure indicates the unit cell of 3 dimension. So simple cubic, this is conventional. When I say conventional, it is nothing but it is a normal primitive cell. So here, so conventional means we are talking about primitive unit cell. And if there are more than one lattice point per cell, you will have an integral multiples, right, of the area of the unit cell. You can just see exactly at the corners. You can just see this particular spheres which is indicated in the figure. So 1, 2, 3, 4, 5, 6, 7, and 8. And exactly at the center, you will have one more atom. So here this particular one more atom or the lattice point. So more than one atom, right, which are residing in the corners. Here extra one atom is there. So exactly this particular atom is residing at the center of the unit cell. We'll just call that as body centered cubic. So this is schematically, this can be represented in this particular format. See here, we are having, this is called non-primitive unit cell because the atom is residing not only at the corners, but also the atoms are exactly at the center. Now, unit cell, so again, okay, now we just we'll understand more precisely how we can know the unit cell geometrically. So geometrically, the unit cell can be known. See here. So the unit cell will have a complete lattice which is having a unique determination of some constants. Here what we are doing, see, when I say unit cell, I'm saying that unit cell is in the shape of a cube. So what is that cube geometrically represented as, mathematically represented as? For that instant, we just take the 3 axes. We just, what we are doing, what I am doing here is that I am extending the lines of the faces, any 3 faces of the unit cell. So here I am just extending it. You can just see this. I have just taken this is the reference point, origin, and I have just extended this particular face here. You can just see here. This face I have extended line. Imaginary line has been expanded. That is the reason it is shown. See, some dotted, you can just see some dotted points here. I am extending this line segment here. That is considered to be x-axis. And here also I am extending. See here. This is the red one until the dimension at the one corner of the unit cell. And here you will find that after this red colored line segment, it has been extended, this red color has been extended with the black line segment, and this particular line segment indicates that there is extra construction, or we can say the extra line which has been extended in the y direction. So this is x direction, this is y direction, and here and the distance between this origin to this particular corner to this particular axis, let us consider that the dimension is taken at small b. These are nothing but the distance between the 2 consecutive points. So that is small a, we have just taken small b, and here origin to this particular phase, we have taken an example of another phase, and we have extended, see, again extended it, and I've just termed it as z-axis. So x-axis, y-axis, and z-axis, and the length of this particular x-axis is a, and this is what b, and this is what c. So a, b, c. So why it is written here x? Why? Because alpha. See here, how I have indicated this angle alpha here. You can just see this particular axis is x-axis. So these x-axis is suspended by an angle, right? Subtended by an angle alpha. Subtended by an angle alpha. And these y-axis here, the negative direction of y-axis, see, you can just, this is the negative y-axis. So this is subtending the angle beta. And here z-axis, you just go inside it, you'll have an this one. This is what? This is your z-axis, and this angle is what we'll call this angle as beta. So here you'll find alpha, beta, and gamma. These are the three angles subtended, right, with respect to the coordinate axes, x-axis, y-axis, and z-axis. So now I think that you have an idea. So why we have just shown you this particular unit cell and how this unit cell can be geometrically represented as. So in order to understand, see why we are going for this particular A, B, C, or I'm extending this particular, extending this line on the x, y, and z axes. Why? Because we want to know the form and size of the unit cell. So the unit cell is determined by the 6 lattice constants. These are A, B, C, alpha, beta, gamma are nothing but we'll just call that as constants. And each corner, you can see how many corners the cube has, cubic unit cell has. Here see, you can just see that 1, 2, 3, 4, right? Right, this is 4, 5, 6, 7, and 8. So how many? 8. So each corner, see here, you can just see, that is the reason that we just, we go to the next figure. This is the arrangement of the atoms inside the any material, solid material. So now you can just see this particular figure, if this unit cell will be like this. So you can just see here, the corner, each corner is having 1/8 part of the lattice point actually be assigned to that particular unit cell. This corner is taking 1/8 part of the lattice point or the atom. So each unit cell in the figure can be associated with how many corners it is having? 8 corners. So 8 corners is what you can taking part? 1/8 part. So 8 into 1/8, 1 lattice point. So this is a simple or primitive unit cell is having 1 lattice point, right? So this is the way that how we can calculate the number of lattice points which are present in the simple cubic lattice. Now this is called primitive unit cell and vectors. Now see here, a primitive unit cell is made up of primitive translation vectors geometrically. Again, you just take an example of geometrical. Again, see, the choice of axes is yours. Now here also, x-axis, you can just, this is taken as x, y, and z axes. Again, the position vectors are taken as a1, a2, and a3. You are getting me? So the primitive, see here, primitive unit cell is made up of primitive translation vectors a1, a2, a3, and such that there is no cell of the smaller volume that can be used building block for the crystal structure. What does this mean? No cell of smaller volume. So the smallest figure that we can draw in 3-dimensionally, this is the case. This is the smallest geometrical figure that you can draw 3-dimensionally. So that is the reason there is no cell of smaller volume that can be used as a building block for the crystal structures. So a primitive unit cell will fill space by repetition of suitable crystal translation vectors. So these vectors is repeated infinite number of times. So just in the previous section we just discussed about what is actually the translation vector is all about. So translation vector deals with the what you can say, a particular function is repeated for infinite number of times. So if you just repeat a particular function by infinite number of times, so whatever the figure that you will get or whatever the function we are getting, that function is known as the translation function, or if I talk about mathematically, that is called translation vector. So a primitive unit cell will fill space by the repetition of suitable crystal translation vectors. So this is nothing but we'll call such figure as nothing but parallelepiped, and a1, a2, a3 are translation vectors. So the volume can be given by A dot, A1 dot into A2 into A3, A2 cross A3. So that is a vector product. And you already know the what the volume of the cell, this unit cell is nothing but it is A cube. Right. Now primitive unit cells here, the primitive unit cell must have only one lattice point and there can be different choices for lattice vectors, but the volumes of these primitive cells are having the same. So here P means primitive unit cell and NP is here. You can just see that how many extent we can just draw our primitive and non-primitive. In the primitive you can just see there are three figures which is showing that primitive unit cell. Here the particular point is unique here, right? So here the particular point here, this is unique one and this is also unique one. So we'll just call this as primitive unit cell. And wherever you find that apart from these corners, wherever you find the extra atom or the point, we'll call such point as non-primitive unit cell. So now we just defined a different types of unit cell and different Bravais lattices, whatever we have observed. So now you'll find that there are, now we just go to our next topic, that is crystal directions. What is actually the meaning of crystal directions? So why we need to understand about this crystal direction? So we choose a lattice point here. What is actually crystal direction? Why we need to understand this crystal direction? Just if you understand this, and then definitely you will come to know why we are studying about the crystal directions. And again, I will definitely try to help you out in understanding this crystal direction by this geometrical figure. So we choose one lattice point on the line as an origin. You can see there a lattice point is there and there is an origin here. So the choice of origin is completely arbitrary, some constant. So every point here is identical to each other. So here we choose one lattice point on the line as origin and say that that particular point, is choice of your origin is some constant. So every point is identical here. So then we choose the lattice vector, which is, see, lattice vector is joined here. We choose the lattice vector joining O to any point on the line. So what I'm doing here is that I'm just joining from O to some point, see, like a line segment. See, you can just see I'm joining this particular line to a point here in the unit cell. So O to T. So just call that as say point T. Now this can be written mathematically as capital R is equal to N1 A bar or N2 B bar plus N3 C bar. Now this is three-dimensional figure, whatever we are observing, right? And here why it is indicated 1, 1, 1. What it means, when you take a graph here, the first point from the origin to the point, right, which is having some what you can say, we've just taken reference 1 meter or 1 centimeter, right? So here just when we see a graph 1 centimeter, you will be from 0 to this particular point, we are assuming that this particular dimension is nothing but it is 1 centimeter. So that is the reason that on the x-axis, this particular, see, this phase is cutting on the x-axis at unit right distance, at unit distance on the x-axis 1, and here also on the y-axis it is having unit distance as 1, and on the z-axis it is having the same unit distance as 1. So that is the reason that here 1, 1, 1 indicates that the intercepts which are made on the x and y axes. So here what is actually the lattice directions? Lattice direction means the points which have been at the corners where you can just know the exact position of the lattice point. So how we can know the exact position of the lattice point? By just assuming this particular line segment, which indicates that here also you'll find a lattice point and here also there is a lattice point. So these lattice points are nothing but what you can say, it is indicating some direction from this particular lattice point to this particular point. So we'll just call that as crystal direction. So distinguish like this lattice direction from lattice point. So what we can say that we are taking just using N1, N2 and N3, and N1, N2, N3 is smallest integer of the same ratio. They will have same ratio with particular ratio, and that particular ratio definitely you will understand when go to the next class or the next session. You can just see here, we have for understanding purpose, we have taken unit cell here. Now I want to locate this particular point here. See here, from the origin to this, what will be the point exactly point? I already told you from here to here, we are just taking it as 1, right? So 1 unit, right, centimeter or 1 centimeter. So here you can just see here this particular arrow mark which has been indicated here. This is what half half line. This line segment has been divided into equal half. So you can just see, let us consider this is completely 1. So here it indicates it has taken the shape of, the dimension is half here. So on the x-axis, see, from here to here x-axis, I can write that as 1. On the y-axis, see, this particular part is on the y-axis. See my arrow, right? Exactly this particular arrow indicates that it is halfway mark. M is at halfway mark. So therefore, y we have written is half. And z we are just writing it as 0. Why we are writing it z as 0? See, here you will not find any intercept here. So here exactly the what we can take it as 0. So here how it has been taken at 0, we have just come to know, right? Here what I am trying to tell is that these are simple examples which are indicating the lattice points directions, crystal directions, right? And this I will explain you by doing on the, right? Physically I will explain you all this thing. Don't worry if you don't understand also, there is no worries. What I do is that I will just draw it and I will show you in depth how this particular things have been came, right, physically. So negative, see here. So when I say integers, again in integers you will have negative values also. So negative directions, when we write these directions n1, n2 and n3 depends upon the origin, and the negative direction can be written as n1 bar, n2 bar, n3 bar. So whenever, for example, this is -1 and -2, see when I say n1, if n1 is -1, I don't write here indicating the direction as -1 here. I will just write 1 bar, 2 bar, 3 bar, -2 as 2 bar, 3 as -3 as 3 bar. So instead of that, generally what we'll write n1 bar, n2 bar and n3 bar. So here r is nothing but the resultant vector. See, for that reason we have just indicated with this particular unit cell. So r is equal to n1a bar plus n2b bar plus n3c bar. So r is equal to n1a bar plus n2b bar plus n3c bar. Now this is the origin, and this is x direction, and this is negative x direction. This is y direction, and this is negative y direction. And here you will find that positive and the negative z direction. So this direction must be a smallest possible integer. So here, so the negative sign, instead of negative sign, we just mark it as some bar here. So this is for the difference purpose. Now, so different crystal direction, you can see that we want to know the different directions, crystal directions. So example, so I will show it by doing, right? Right, in the next session, we'll just I will do it and I will show you on the on the screen, right? Okay, so you'll not have any problem, right? Don't worry, you should not have any worries regarding this particular figures. Okay, now when we go for the crystal, just now we learned that how the crystal directions look like geometrically. Now we just go what is actually the meaning of crystal planes. When I say planes, how that planes look like. So within the crystal lattice, it is a possibility to identify the sets of equally spaced parallel planes. Planes, what does actually planes means? This is x-axis and this is y-axis. So this indicates this is one plane. This is another plane. So we call it a set of equidistant planes. So these are called lattice planes. So again, see, again I'm repeating, right, for your understanding purpose. This one set of lattice points, and this is the different another set of the lattice point. And in another set, you can just see here, this particular arrangement is something different, two-dimensionally. See, first we talk about two-dimensionally, then we go for the three-dimensional, how the planes look like. So here, this is one arrangement of lattice points, right? And this is another arrangement of the lattice points. When you arrange the lattice points, how the planes will look like in x and y direction. Say like this. Here, this particular distance is nothing but a, and this distance is b. Here also, here the distance is a, and here the distance is b. So this is called a set of planes in two-dimensional lattice. So like this, you can just imagine that you can just draw different types of planes here. So in this figure, so we can know the density of lattice points on each plane of the set is same, and all the lattice points are contained with on each set of the planes. What is actually this? We are talking about density. Why we require density? See, we require density to locate the atoms or the molecules or the ions where you will find the large concentration of these constituent particles. So such that if you find the large concentration of particles, then you can incident the light radiation, and when you incident the light radiation, you will get an image. For example, my hand has been fractured. So in order to understand this lattice, why we are going for in detail, let us consider my hand got fractured. So what I will go to the doctor and I will say that this particular, I am unable to, right, movement, there is no movement in my fingers, so I am unable to do some, no operation has been done by my fingers. So what I do, I will tell the same thing to the doctor, and doctor say you just take an X-ray and come again. So when you go to the X-ray technician, he will just take the X-ray of my fingers, and whatever the X-ray image you will see, that image indicates, see, image doesn't specify the mass. It will take only the hard part of the body. So that only bones part the image can be, whatever the image you are seeing on the X-ray, that is right, bone part is saying. And what it indicates, wherever you find that there is a hard part, it indicates that the concentration of atoms are more. For example, I am just taking an example of that X-ray. So that concentration of atoms are more on that particular region. So that indicates that the crystal planes are indicating that the concentration of lattice points are more. See here, the concentration of lattice points are more when you geometrically draw this type of figure. So that is called crystal planes, right? So why we need to understand these crystal planes? You need to understand the crystal planes in order to define the next topic, that is related to Miller indices. So what is actually the Miller indices? So Miller indices is nothing but, see, what is the aim of our aim? We want to locate the atoms inside the solids, atoms, molecules or constant particles, where you will find large concentration of atoms. Then we will incident the beam in order to study the structure. So where are that concentration of atoms or molecules or the ions are there? So they will be, how can I get that particular value? See, mathematically that can be shown by crystal planes or crystal direction will give me the idea regarding the concentration of the atoms. So Miller indices here are nothing but a symbolic vector representation which have the same ratio as their reciprocals, right? So what is actually Miller indices? If you want, you can just write it down, make a note of it, that Miller indices are three smallest possible integers. They are smallest possible integers, and that smallest possible integers are having the same ratio as their reciprocals. They are having the same ratio as their reciprocals. See, again I am repeating, Miller indices are smallest possible integers which are having the same ratio as their reciprocals of the concerned axes. So Miller indices are symbolic vector for representation for orientation of atomic plane in crystal lattice, and they are defined as the reciprocals of the fractional intercepts which the plane makes with the crystallographic axis. This is one way of defining it, right? So if you find any difficulty in understanding this particular definition, you can just simply write so that Miller indices are nothing but they are the smallest possible integers, three smallest possible integers. So why I am writing three smallest possible integers? I am talking about x-axis, y-axis and z-axis. So it is the smallest possible integers which has the same ratio as their reciprocals of the concerned planes on the crystallographic axes. We will call simply that particular arrangement as Miller indices. Now how you can know the Miller indices of the given crystal? So to determine the Miller indices of any plane, see, when I say plane, you can just see this is one plane. See, you can just see this cubic three-dimensional structure, smallest unit cell is cubic in nature. So now you can just see that this is intersecting this particular format. See, this is in this particular format. So now this is indicate this is one plane. This is completely one plane, right? Right? This is one plane. Now see here, this is one plane. So you see, to determine the Miller indices of a plane, taking the following steps. So now I want to know the Miller indices of this particular plane. See here, you can just take example of this, any unit cell. This is one part on the x-axis. So what I would do is that, so now determine the intercept of the plane along each of the three crystallographic directions. See, how I can know mathematically know that Miller indices of a given plane. So that plane may be faces of that planes. If I talk about plane, that is nothing but which are having I'm talking about the cubic unit cell, and that is having some 6 faces. So if you want to know what is the Miller index of a particular face, right, you can just see a dice. Dice is having how many faces? 6 faces. It is in the shape of a cubic, right? Cubic shape. It is a cube in nature, cubic in nature. So one face, if you talk of one face, one axis. Another face, another axis. Third face, third axis. X-axis, Y-axis, and Z-axis. This is for your reference in order to make it very simple. So how I can determine this Miller indices? So the Miller indices can be defined very normally. This can be determined intercepts of the plane along each of the 3 crystal directions. First, you have to determine the intercepts of the plane. Plane, face, one face. Just take one face. So determine the intercepts of the plane along each of the 3 crystallographic directions. Now, whatever the intercepts you observe, that intercept, you just take the reciprocal of that intercepts. So take the reciprocals of the intercepts. And then, if whatever the fraction you are getting, multiply each of that particular fraction with the denominator of smallest fraction. What is the meaning of this? If in fraction results, multiply each by the denominator of the smallest fraction. Here, just we have taken, see, for you, we are just taking an example. So intercept point on the x-axis is 1. You can just see. I am talking about this particular plane here. So intercept, this is the reference point origin. It has been intersected. So this particular point has been intersected here. So we have just taken it as 1. See, I am talking about this plane. So this plane, this face is parallel to y-axis, and also it is parallel to z-axis. See, this shape or the image or the pattern is parallel to y-axis, and also this is parallel to z-axis. So intercept point, what is the intercept which is made on the x-axis? You can just see this plane. Again, the plane is making the intercept here x-axis 1. On the y-axis, it is parallel to another axis. So parallel to any, if the plane is parallel to any of the axes, we'll just take it as infinity. You already know parallel lines never meets, and they meet at infinity. So this particular plane is parallel to y-axis, so we'll just take it as infinity. And also this plane is parallel to z-axis, so that is taken as infinity. You can just see, determine the intercept of the plane along each of the 3 crystallographic direction, and then take the reciprocals. I have taken, see, 1 by 1, 1 by infinity, 1 by infinity. So this 1 by 1 is smallest ratio 1. 1 by infinity 0. 1 by infinity is 0. So here whatever the smallest ratio I have given it as, that smallest ratio is given as 1, 0, 0. Right? See here, the numerous number of examples I am having. See. See, first example, see 1 by 1, 1 by infinity, 1 by infinity, 1, 0, 0. So what is the Miller indices? Miller indices designated, see, if I write comma, that is not Miller indices. That is only points. So Miller indices are what? 1, 0, 0 is Miller indices. Okay, this is example 1. Now example 2. See, 1, 0, 0 is over. Now I am talking about this particular plane. See, this face, which is, see, this plane, we am talking about this plane here. Example number 2. This is the plane. You can just make a note of it. So I will wait for some time. So if I am talking about this plane, see, this plane. This plane. You can just see, it is intersecting at this point y direction, right? I'm talking about this particular point. Here, on the y-axis, this particular plane is intersecting here. So on the y-axis, what I have written? Y. On the x-axis, see, you can just see, on the x-axis, this particular plane, I'm talking about this particular plane, it is intersecting. So it is intersecting at a point 1 again for the y-axis. X-axis, see this, I'm talking about this particular point, and here x-axis you will have a 1, y-axis you will have 1, and then at the z-axis it is parallel to each other. So therefore we will just take it that is as infinity, 1 by 1, 1 by 1 and 1 by infinity. So 1 by 1 reciprocal 1, 1 by 1 1, 1 by infinity is 0. So what is the Miller indices? 1 1 0. I cannot write comma here. If you write comma, then it is called points. It is not Miller indices. Indices means that it is we talk about the designation with respect to planes. So therefore, planes cannot be designated with points. So 1 1 0. So like this, you can just have an example. See here. If it is this 1 0 0, this I am talking about 0 1 0. If this is the case, this is 0 0 1. Like this, you can, if I talk about all these complete unit cell, so what will be the Miller indices? 1 1. Why? Because see, I'm taking reference point at 0, and it is exactly intercepting at 1 here. Here from here it is intersecting at point 1 here on the y-axis, and from here it is exactly intersecting at a point 1 here. So x-axis 1 unit, y-axis 1 unit, and z-axis it is 1 unit. So like this, you can make a note of, see, if this intercept, if it is indicated with C plus, I have written here. If it is intercepting in the here, so this I have to take it as a half. So like this you have to do, see, intercept half, here 1, and here this is parallel to z-axis, therefore it is taken at infinity. 1 by 2 is already there. So reciprocal of 1 by 2, 1, 1 by 2, that will give me 2, 1, 1 by 1, 1, infinity, 1 by infinity is 0. So whatever the value will get 2, 1, 0, this is the example, fourth example. And here, see here, for again, see, we just discussed about different planes here, different planes, and now this is more, you can easily understand this, right? Now we have taken 3 axes very clearly with different lengths. See, let us consider this is x-axis, this is A, see here, this is A indicates this particular thing is A x-axis, B is y-axis, and here C is the, this particular indication is here z-axis, x, y, z, A dimensions, A, B, C, lattice constant. These are called lattice constants, arbitrary constants A, B, and C. So here, from origin to here, we have marks here. This particular thing is nothing but 1, 2 units, 3 units. So therefore, we have written what is the length? A bar. So 3A bar, here 2, 2B, here 2C. So 3A bar, 2B, 2C. And you just take a reciprocal of it, 1 by 3, 1 by 2, and 1 by 2. So just 3, 2, 2, you take the LCM of 3, 2, 2, you will get, right? What you will get? 6. See? 1 by 3 into 6, 1 by 2 into 6, 1 by 2 into 6. So 1 by 3 into 6 is 2. 1 by 2 into 6 is 3. 1 by 2 into 6 is 3. So what is the Miller indices? 2, 3, 3. So we are just whatever the reciprocal you will get, you take the LCM of it. Solving, simplifying means you just take whatever the LCM you will get, denominator values, whatever the values you are getting, just take that reciprocals, multiply it with this particular term, first term, 1 by 3 into 6, 1 by 2 into 6, 1 by 2 into 6, you get 2, 3, 3. And this is the Miller indices of plane, right? And indices of the direction. So Miller indices of the plane. See, so points 2, 3, 3. And when I say Miller indices, it will not have these commas. So Miller indices, directions. If you indicate directions and planes, you'll with this particular values will write. If I say only Miller indices, you can just see. So different shapes for you. See here. Why this is a cubic unit cell. So I want the value of Miller indices of only this particular part. Therefore, it has been shaded with yellow. So it is 1 0 0. Here it is 2 0 0. Right? 2 units. Here it is, I'm talking about with respect to x-axis only. See here, it is cutting x-axis. It is also cutting x-axis. Here also x-axis. Here also x, y, and here x and y. Here, this particular yellow portion. It is a plane. Yellow portion is plane. Here also 1 1 1 is a plane. So now we just discuss about the Miller indices and so on, right? So we'll go over the typical crystal structures, the different types of crystal structures which are there. So here we'll just know that there are in 3 dimension, there are 14 types of Bravais lattices and 7 crystal system which is available on the earth crust, right? In 3 dimension how many? In 2 dimension we just discussed about 5 Bravais lattices, and 3 dimension you'll find that there are 14 Bravais lattices, and these 14 Bravais lattices are classified in 7 crystal system. So what are the 7 crystal system on the earth crust that we'll find? Cubic crystal system, which is having simple cubic unit cell, body centered cubic unit cell, face centered cubic unit cell, hexagonal, triclinic, monoclinic, orthorhombic, tetragonal, trigonal crystal system. So these 7 crystal system, which we'll find that the solid materials, crystalline solids are available on the earth crust, and in that crystal systems you will find different Bravais lattices, and that we call Bravais unit cells. So in crystal, particularly crystal unit cell, you will find simple cubic, body centered and face centered. So this type of, you see this A, B, C, alpha, beta, gamma together are known as lattice parameters. A, B, C are constant, alpha, beta, gamma are interfacial angles, So if these particular what you can say parameters are showing this condition is satisfied, then we can call this particular unit cell come under the category of cubic. So okay, you can just have a look of it and you can just make a note of it, right? Please make a note of all this. You don't draw this particular figures here. You can just make a note of this particular parameter: cubic, tetragonal, orthorhombic, hexagonal, monoclinic, and triclinic, and also triagonal. So how many? 1, 2, 3, 4, 5, 6, 7 crystal system. The schematic diagrams of the different what you can say unit cells which are available on the crystal system. Understood, everybody? Now you just make note of it. See, this particular thing is again we'll be repeating this one. If you want, right, we'll conduct a meeting, Zoom meeting, and then we'll discuss if you don't understand anything, right? We'll start from fresh. And no worries, please. And this particular video, you can just pause it and you can just make a note of it, right? Thank you everyone for listening patiently. Now again, this part I will show in the later section.